let's start off with a video about zombies.
Last Tango in Halifax returns.
Wonderful.
Oh, wonder who that is. Yeah, what's up? What's up? Too close. Too close. Whew. Wish me luck. Always knew this calculus book would come in handy. Typical zombie behavior. Instead of running across the front and up the stairs like any rational human being would do, they don't have the brains in their head to do it that way. Instead, they have to come straight for me, straight up the chairs. It's going to take them a half hour to get here. All right, well, we better get going. Okay, we are up here on the roof of the Science Center. I think we're safe from zombies up here. And you might have noticed what happened down there in the auditorium. A little bit scary, but it worked out okay because zombies head straight for their target, which in this case was me. And so therefore, that's going to bring them straight over the chairs, which is one of the worst things that they could do for their sake. Now, we can describe that using one of the concepts from calculus called the tangent vector. The idea is very simple. If you have any object that's moving along a curve in space, the tangent vector will be an arrow that is just touching the curve and is what we call tangent to the curve, pointed in the direction of motion at a given instant. And as that particular object moves through space, that tangent vector moves along with it, always pointing in the direction of motion. In the case of the zombies, that vector, that arrow, is always pointed toward the person that the zombie is chasing. And that completely determines the path of the zombie. In fact, if you look down here right now, you can see a case, there's somebody running from a zombie right there, and you'll notice that the zombie is always heading straight toward the person. So if you think of that zombie moving along a curve that is the path that it's taking, then its tangent vector, that arrow, is always pointed toward the person that the zombie is chasing. And the zombie's never going to catch the person because it's always pointed towards where the person just was, not where the person's going to be by the time the zombie gets there. And the zombie never knows to cut them off, and you can use that to your advantage just as I did down in the auditorium. Good, it looks like they're going to be safe.
Get away, zombie maggot.
Now, this idea of tangent vectors turns out to be very useful in a lot of contexts. For instance, if we're looking at the space shuttle and trying to get it to dock with the space station, you use it when you're trying to get satellites to a particular orbit. This turns out to be a very useful concept. Oh! I see some people down there look like they're in trouble. Look, I'm going to see if I can go help. So I'm going to ride my bike and see if I can help them. So let's see what we can do here. Of course, safety first. Let's get the helmet on. All right, I'm going to try to attract the zombies to me. Here we go. Wish me luck. Let's see what happens. All right, you zombies. Hey, follow me. Come on, you zombies. Follow me over here. Come on, you're not so smart anymore. You used to be academics. You're not anymore, are you? That's good. Good, zombies. Come on. Working like a charm. Nothing like an afternoon bike ride with a bunch of zombies behind you in a pack. I'm riding in a big circle around the quad right now. So you notice they're starting to follow me. They're starting to group together. And the idea is that the zombies are always going to head towards where I am. And what that means is their tangent vectors are always pointed straight at me. Now, because of that, it turns out that no matter where they start, they end up actually grouping in a clump, and they end up following me on a circle that has a smaller radius than my circle. So my circle's bigger than theirs because I'm riding faster than they're moving. But I end up getting all of them to follow me. So eventually, they'll be all together, in which case these people can escape. All right, the zombies are following me. Okay, you folks, I think you're clear. You can get out of there and get to safety as quickly as possible. All right, looks like they're good. Now I just gotta get to safety. So hang on just a second. I'm gonna bring it around. Come on, you zombies. Okay, so this is the end of my video. I hope you've learned some things that you'll find useful. Maybe math will save your life. And I wish you good luck. I gotta get inside. Drop the bike, we're out of here.
All right, so some more useful tidbits about derivatives and these differentials. So here we go. So let me just double check this. I want to make sure that this is going to fit our screen nicely, so we're not missing a bunch of it. So hopefully this shows up for you. So remember from quadratics, we had a problem like this way back in the day, and we wanted to maximize area. And now that we know derivatives and we know that we can calculate the first derivative and find where it's equal to 0, and we'll find maximums and minimums are extrema, we can use that skill now, and it's going to save us a lot of time. So we're just going to find where the first derivative is equal to 0. And that can help us maximize our area. In order to be super successful at these problems, make sure that you're reading each one slowly and carefully. If you misread it, you've lost all hope and you won't be able to solve it correctly. Don't be afraid to draw. If I can draw, you can draw. Define your variables and label the drawing that you've created. Write down all your equations related to your problem. Usually there's going to be 2. One's going to be a constraint equation used to solve for one of the variables, and the other one will be the optimization equation used to solve the problem. Before you differentiate, make sure that the optimization problem has only one variable. There we go. We're going to verify our result using the first or the second derivative test for extrema. Some more. And here we go. Let's get to solving. So here we've got a rectangular cake dish. Manufacturer is going to be making their dish by cutting out squares from the corners of a 25 by 40 centimeter rectangle of tin. And then they're going to fold it up to form the box like it's shown here. So what size should the squares be cut out in order to produce the largest dish possible? So if we've got this picture, I'm going to be cutting out, let's get rid of this guy here, some amount. I'm not really sure what it is. I'm going to call it X, length of X and a width of X, little squares. And I do know this whole entire length here is 40, and this length here is 25. When it's all folded up, the height of this thing is going to have a height of X. The length is going to be 40 minus the 2 X's that I cut out from the corners. And then this length here, the width, is really going to be 25 minus 2x because we cut the x's out from these corners here. So we'll have x be the sides that are cut out. Don't forget that volume is our length times width times our height. And in this case, the length is 40 minus 2x. The width is 25 minus 2x. And our height is x. So we end up getting that volume is equal to 40 minus 2x times the quantity 25 minus 2x times the height, which was x. And we can multiply these all the way through, and I get that my volume is 1000x minus 130x squared plus 4x cubed, and this is all in centimeters cubed, right? Because length times width times height would give us our units cubed. So here's what we know. We know that x has to be greater than 0. Obviously, if we're cutting something out, it's going to have to at least be something. We also know that 40 minus 2x has to be greater than 0 because this whole length should be positive. Similarly, 25 minus 2x has to be greater than 0. And if I solve these little mini equations, or inequalities I should say, well, let's subtract 40 from both sides. I get negative 2x is greater than negative 40. I'll divide by negative 2. This is going to flip my inequality symbol, and I get that x has to be less than 20. Over here, I'm going to subtract 25. Divide by negative 2. And I get x is less than positive 12.5. So if x is bigger than 0, which it is, and it's also less than 20, and it's also less than 12.5, what that means is that x has to be in between 0 and 12.5. All right. So let's go ahead and calculate that rate of change, how it's changing depending on how big our x value is or how little. So I'm going to take dv dx, take the first derivative of our volume equation, and that's going to give me, let's see, the derivative of 1000x is 1000. The derivative of 130x squared is 260x minus sign. And the derivative of 4x cubed is 12x squared. So you can find the zeros by factoring, by grouping, using polysimult. I would say set it equal to 0 and polysimult. And when I did, I got two results. I got x was equal to 50 thirds, or x was equal to 5. Now 50 thirds is approximately 16.6 repeating. But I just figured out that x has to be in between 0 and 12.5. 16.6 is way too big. If we cut out chunks that were 16.6, think about what that would mean. 16.6 across here and another 16.6 across here, well, that would overlap and there would be nothing to fold here anymore. So that's way too big. This is what we call an extraneous solution. Yes, it's a solution, but in the context of our problem, that's not going to work. So the only solution that's kind of within the realm of possibility is this x equals 5 solution, since this one was just too big. And from here, we can use sine diagrams or the second derivative to see if it's a maximum. Because remember, we're trying to find the largest dish possible. When you see that largest thing, that's an optimization problem. And we're trying to determine if this is a maximum or a minimum. So let's go ahead and try a sine diagram. So if I tried a sine diagram, I would have my dv dx, and we are in between 0 and 12.5, and 5 is somewhere over here, and I can test some values. If I test 1, I'm going to get a positive result by substituting into my derivative equation. If I test 10, I'm going to get a negative result. So what that means is that my graph is increasing, increasing, increasing until I get to 5, and then I start decreasing, decreasing, and decreasing. This is a maximum. So that means that my square's length has to be 5 centimeters in order to maximize the volume. I have to cut out little chunks that are 5 by 5 chunks to maximize the volume of this tin. Now I can also use the second derivative test, so we can try that. D squared of v dx squared, our second derivative, is equal to, well, the derivative of 1,000 is 0. The derivative of negative 260x is negative 260. The derivative of 12x squared is 24x. If I set that, if I solve that, negative 260 plus 24 times 5, I get negative 260 plus 120, which is negative 140. That is less than 0. What that means is that we're concave down at 5. And if we're concave down, then what we have is a maximum. So either way, we've got a max where x is equal to 5. And there we go. All right, problem number 2, another type of box situation. So this question, I know my drawing isn't the best, so I apologize for that. We've got a box that has a square base, so maybe I can adjust this so that it looks like we have a square base. Well, I don't know about that. I can attempt to draw one for you. Here we go. Oh, I apologize in advance for what you're about to experience. So we want to start off with a square base. It's square-ish. And then it's going to be a rectangle. Here we go. And here. So this one looks more like it has a square base and then rectangle sides. Okay. Now, if my base is square, then this side and this side are going to be the same. And if my sides are rectangles, the heights are going to be y. If the area of this thing, remember it's open top, so it's got a bottom but not a top, the area has to be 48 meters squared, because that's how much plywood we have available for it. And that's basically the area of the base, the square base, plus 4 areas of the sides. So if I have this base here, the base is going to be x squared. That will be the area of that. And the 4 areas of the sides, well, the side is a x by y, so there's 4 of those, so 4xy. And that's going to have to add up to give us 48 meters squared because that's all the materials that we have. A good thing to try and do here would be to solve for y. So let's get the y alone. So I'm going to have 48 equals, let's subtract the x squared to the other side. So 48 minus x squared is equal to 4xy. And I'll divide both sides by 4x. You might be wondering, why would I do that? It's a lot easier to work with these things when you have solved for one variable already. So I've got y is equal to 48 minus x squared divided by 4x. Each time I make a 4, it really wants to have this line go across there. So that is a 4, not a 9. All right, so volume is length times width times height. We're trying to maximize the volume here, even if we do not have the top on it. Our length was x, our width was x, it was our height that was y. And so this is really x squared times y. And of course we know what y is now, since we very conveniently solved for y already. It's 48 minus x squared divided by 4x. So I'm going to substitute that in here. So my volume is equal to x squared times 48 minus x squared divided by 4x. We can reduce this because I've got an x on top and an x on the bottom. And I get that the volume is equal to, and I'm also going to distribute this x, the leftover x there. So I'll end up with 48x minus x cubed all over 4. What we're going to do is break this down a little bit more. So I've got my volume is equal to, well, 48 divided by 4 is 12, so that would be 12x minus 1/4 x to the power of 3. At this time, I'm going to start by taking the first derivative because I've got to maximize the area. I want to find where the maximum is of this graph. The derivative of 12x is 12. The derivative of negative 1/4 x cubed is negative 3/4 x squared. And I can set that equal to 0 and solve it. I'm going to add 3/4 x squared to the other side. And I will multiply by 4/3 to get my x squared alone. And I get x squared is equal to, let's see, 3 goes into 12 4 times, and 4 times 4 is 16. Oh, this turned out nice. Take the square root. Now, I know that the square root of 16 is positive and negative 4, but I'm only going to need the principal square root, the positive one, because I can't have negative sides of this, this box. So we've got x is equal to 4. If x is equal to 4, then we can find out what y is equal to. Remember, y was equal to 48 minus x squared divided by 4x. So I would get 48 minus 16 divided by 16. Well, 48 minus 16 is 32, and 32 divided by 16 is 2. So if x is equal to 4, then y is equal to 2. Let's check out with the sine diagram. If I tested 3 by substituting that into my first derivative. 3 squared is 9. 9 times 3/4 is smaller, and 12 minus the smaller number is going to give me a positive result. If I substitute in 5, 5 squared is 25. 25 times 3/4 is a pretty big number, and 12 minus that larger, it's going to be larger than 12 anyways, is going to be negative. So as I approach 4, we are going to be positive, and after 4 will be negative. That, my friends, is a maximum. So we have a max volume at x is equal to 4 and y is equal to 2. So wider base, less height. How about a llama? Before we do the llama problem, sometimes the variable that's going to be optimized is in the form of a single square root function. In these situations, it's convenient to square the function and use the fact that if a of x is greater than 0 for all x in the interval under consideration, the optimum value of a of x occurs in the same place where a of x squared will also take place, the whole quantity, the whole function a of x. So I'll show you what I mean here in the llama problem. Okay, so we're going to build this llama enclosure, and it's going to be a triangle shaped enclosure. We're going to use the fact that the topography already has a drain in place from A to C. So we're going to not have to put any fencing there. Instead, we can use 300 meters of fencing to make this beautiful triangle shaped pen for the llama. So they're telling us right away that, hey, AC, the length of this drain, is the square root of 90,000 minus 600x if AB is equal to x. So what we need to do is actually show that that's true. I would say that if I'm going to use 300 meters of fencing, so the AB and BC is going to be where the fence is, I can call this side x amount of fencing, and I could call this side 300 minus x, or vice versa. It doesn't really matter which one I call x and which one I call 300 minus x. But what I'm going to do is I'm going to show, using the Pythagorean Theorem, that the missing side is really 90,000 minus 600x, the square root of it. So here we go. Let's try it. I know that a squared plus, let's call this AC squared, is equal to 300 minus x squared. The legs of the triangles squared and added together is equal to the hypotenuse of the triangle squared. And I can extend this out a bit. It's not too bad. 300 minus x squared is 90,000 minus 600x plus x squared. And the cool thing is that if I subtract x squared to the other side, it'll cancel the other x squared out, because any number minus itself is 0. Then what I have left is AC, the length of that drain squared, is equal to 90,000 minus 600x. And hopefully you can see it happening. We're just going to take the square root to get AC alone. So in fact, it's true, the length of that drain is the square root of 90,000 minus 600x. So that's the first part, that's part A. Make sure you recognize we're rejecting the negative solution that we would get when we take the square root, because it's impossible for the drain to have negative fencing. So now question B asks us to find the maximum possible area. Well, when I see that keyword maximum, that's when I know I have to take the derivative and set it equal to 0 so I can find the maximum of the problem. So let's go ahead and take care of that. Remember, the area of a right triangle is 1/2 times the base times the height. So in this problem, the area is equal to 1/2 times our base. The base was AC, so that's the square root of 90,000 minus 600x. 1/2 times the base times the height, and the height of this thing is x. Now, I want to take the derivative, but this is going to have some interesting effects. I'm going to have this raised to the power of 1/2 multiplied by x, doing the power rule. It's going to get a little wild. So what I'm going to do is I'm going to square everything. When I square everything, I'm going to square both sides. My maximum is still going to be in the same spot. Okay, so we're going to square everything. So I'm going to get a squared, 1/2 squared is 1/4. A square root times this being squared, cancel each other out. And x is also being squared. If I distribute this all the way through, which I will, distributive property is awesome. So distributing 1/4 as well as x squared to both terms here, I'll get a squared is equal to 22,500 x squared minus 150 x cubed. What I'm going to do now is I'm going to take the derivative on both sides. As I haven't taken the derivative yet, I'm just trying to simplify and set up. So we are now ready to take the derivative on both sides. Okay, I'm going to set my derivative equal to 0 and solve it and see what I get. So don't forget, the maximum value of a squared is going to be the same, the x value of that maximum value is going to be the same as on the original function. So I'm going to get 45,000 x. 3 times negative 150 is negative 450 x squared. And we're going to set it equal to 0 to find our maximum value. You might notice that they definitely have some things in common. So we can factor out 450 if you like, or you can use polysimul, it's up to you, as well as an x. And this is going to give me 100 minus x. If I set this equal to 0 and solve with the zero product property, either x is equal to 0 or x is equal to 100. Now, it doesn't really make any sense whatsoever that this enclosure would have an x value of 0. I mean, that poor llama would have nowhere to go. So obviously that's an extraneous solution. It's nonsense. It works mathematically, but not in the context of the problem. So that's extraneous. We don't need that. So that leaves us with x is equal to 100. So let's check it out and see what's happening at 100. So, because it is asking us to find the maximum possible area. So it happens when x is 100. So we can prove that with a sine diagram. So we can say, here's 100. We know that the maximum amount of even fencing that we had was 300, although we wouldn't have been able to use all 300 as x. But if I tested a value, I think I tested like 25 by substituting it into the first derivative equation, I got a positive result. And then when I substitute in like 125, I got a negative result. This is going to give me a maximum. And so we can find the area out by going 1/2 times our height, which was 100, times our base, which was, the square root of 90,000 I'm gonna run out of room, times 600 times 100. And this is gonna give me 8,660 meters squared. So this is our maximum area. Okay, so let's try this next one. Here we've got a picture book that has pages with this area, 672 centimeters, top and side margins of 3 centimeters, and a bottom margin of 4 centimeters. So let's set it up how it's probably gonna look. So we've got our page. Looks like that. The top margins gonna be 3, the side margins are gonna be 3, and the bottom margins gonna be 4. So it'll kind of look like this. So the space between here is 3, the space between here is 3, the space between here is 3, and the space between here is 4. What should the dimensions of the page be? So the greatest possible area is available for pictures. We want this space to be maximized. It's got to be the greatest possible area. So I don't know what this length is. I'll call that X. I don't know what this length is. I'll call it Y. And on the inside, the part that I'm going to maximize, this length here is X, but it has been subtracted by 3 here and subtracted by 3 here, so that'll be X minus 6. Now this length here is the whole length of Y, but it's being subtracted with 3 and with 4, so that's going to be Y minus 4. I'm sorry, minus 7. Minus 4 here, and then minus 3 here, so that's minus 7. So I got X minus 6 on the inside by Y minus 7. I also should know that X times Y, the dimension of the pages, has to equal 672 centimeters squared. And we're going to go ahead and solve this for one variable. It doesn't matter which. I have a tendency to solve for Y. So that's what I'm going to do. And I get that Y is equal to 672 divided by X. That's just for the outside of the pages. Remember, we're trying to maximize the inside, the picture area, that printed part. So the printed part is having a width of X minus 6 and a length of Y minus 7. We already figured that. But we also now know that Y is 672 divided by X. So that's really 672 divided by X minus 7. Okay, so the area of the printed part, so I'll call that A sub P, the area of the printed part is X minus 6, the width, times 672 divided by X minus 7. That's our length. Width times length. Width times length. And we can multiply this all the way through, and I will get X times 672 divided by X is 672. X times negative 7 is negative 7X. Negative 6 times 672 divided by X is negative 4,032 divided by X. And negative 6 times negative 7 is positive 42. And I'll go ahead and do 672 plus 42. So we've got the area of the printed part is 714 minus 7X. And I'll move my x into the numerator position just by changing the sign of the exponent. So that's going to be minus 4032 x to the negative 1 power. So now I'm going to find the maximum, my extrema. So let's move this up a bit. I need the first derivative for that. So let's get started. The first derivative of the printed area, well, the derivative of 714 is 0. The derivative of negative 7x is negative 7. And the derivative of negative 4032 x to the negative 1 power is positive 4032 x to the negative 2 power. I'm going to set that equal to 0 and solve. And I moved my x squared down to the denominator and made it positive. I'm going to add 7 to the other side. And I'm going to multiply both sides by x squared to get that out of the denominator. Of course, now x squared is not alone. It's getting multiplied by 7. So I'm going to divide both sides by 7. And I get that x squared is equal to 4032 divided by 7. When I take the square root on both sides, I'll get that x is equal to plus or minus 24. Now, obviously, the negative result is talking about a negative area on a page. That doesn't make any sense. So we're going to keep the principal solution, which is 24. And we're talking about centimeters here. If x is equal to 24, then we should be able to find out what y is equal to. But let's first see if it's a maximum or a minimum. So let's come over here and do a little sine diagram. I love sine diagrams. So where x is 24, we can also test out 23 and 25. Why not? When I substituted 23 into the derivative equation, I got 0.62, which was positive. Very small number, but positive. When I tested 25 by substituting that in for the x here, I got negative 0.548, and that's a negative result for sure. So as we hit 24, we were going positive, but then we went negative right afterwards. So this is a maximum. And we knew that y was equal to 672 divided by x. So if x is 24, y is equal to 672 divided by 24, and that would be 28 centimeters. So our final result is asking us for the dimensions of the page. So the dimensions should be 24 centimeters by 28 centimeters to have a maximized area. All right, and here's our final one. Kind of love this problem. A piece of wire that's 100 centimeters long is divided into two pieces. One piece is going to be used to form a circle, the other a square. So we've got 100 centimeters length of wire cut into two pieces. One part is going to be folded into a square. One part's going to be folded into a circle, but all from 100 centimeters of wire. So I don't know how much is going to be used for the square part. I'll call that x. So that means that if the whole thing is 100 centimeters and x part is used for the square, 100 minus x is going to leave you the circle piece. So if the whole, we know that the area for a square is we take the side of the square and we square it, right? We also know that the perimeter of a square is 4 times the sides. that means that a side, if the perimeter, the whole distance around, is going to be this length of x, we can divide both sides by 4. And we get that s is equal to x over 4. With the circle, we know that the area of a circle is pi r squared, and we know the circumference of the circle is 2 pi r. And the circumference is the whole length of the wire that's going to be used for the circle. So that's 100 minus x is equal to 2 pi r. In the formula for the area of a circle, I need to know what r is. So I'm going to divide both sides by 2 pi to get my r alone. So I get r is equal to 100 minus x divided by 2 pi. Now, the area of this whole thing is going to be maximized. We're talking about the combined area. And we're not going to maximize it. We're going to minimize it. Very good. All of our other examples have been maximums, so this will be fun. So the area is going to be the area of the square, which is the side squared, plus the area of the circle, which is pi r squared. And we know that s is x divided by 4. And we know that r is 100 minus x divided by 2 pi squared, of course. And we can simplify this up. So I'll get that the area is equal to x squared divided by 16 plus, let's see, my pi will cancel out one of the pi's down there. This is going to give me 100 minus x squared divided by 4 pi. Now I'm going to try and minimize. To minimize, again, I'm just looking for, oh my goodness, Mrs. Rajewski. So I'm going to take the derivative. I'm going to find out where it equals 0. I'm going to test it to make sure that I have a minimum instead of a maximum. So first derivative, I'm going to get 2x divided by 16 plus 2 times 100 minus x to the first power divided by 4 pi. And then, because of the chain rule, I have to multiply by the derivative of what's inside. So that'll give me -1. Simplify that, tidy it up a bit, and I get 2/16 reduces to 1/8, so I get x over 8. And over here I can just distribute this, and I've got -100 plus x over 2 pi. All right, we're going to set this equal to 0, and honestly, I would graph it to find what values you get for 0. And after graphing that on my calculator, I got 56.01. But is it a max or a min? So this time I'm going to do the double derivative. So the second derivative is going to give me 1/8. And if I take the derivative of this, I'm just going to get 1 over 2 pi. And it does not matter like what x value, the whole entire thing is going to be positive. This whole thing is positive. So this is concave up. Since it's all positive. And concave up looks like this, that is a minimum. So we definitely have a min. So our square has and is going to use 56.01 centimeters of that wire. And the circle is 100 minus 56.01, which is about 43.99 centimeters. So darn close. And that's it. That's what I've got for you. So please make sure that you go ahead and do the homework, the reading assignment. Oops, not this one. So we're going to go into Cognity and do the reading assignment for both 7.5 and 7.5, the actual homework. Best of luck to you, my dears, and I'll see you next time. Bye-bye.